Okay, section 5.3, kind of our last foundational section to where we get what you might call the shortcut to doing what we're going to define here, the definite integral. So the last thing we said in the last section was Riemann sums. And so we said a Riemann sum for a function y equal f of x over an interval a to b is formed by selecting a partition, x0, x1, x2, x3, blah, blah, blah. And all a partition is taking your interval and whacking it up into subintervals. And so all these x's are just each one of the x coordinates that we just took this interval and whacked it up into pieces. So it's all a partition is. You've just broken up a big interval into a bunch of subintervals, such that x naught is less than x1 is less than x2, and so on. Then for c sub k in each subinterval. So c sub k is just some number in each one of these intervals, where that c sub k could be the left-hand endpoint, looks like it's about the midpoint. Here we're back to the left. Here, a little bit more than a midpoint, but the point is that c sub k is just any number in that interval. It doesn't have to be left, right, middle. It can just be anywhere. So then for c sub k in the subinterval, and that's supposed to have an x there. That's a little typo right there that I'll have to fix someday. That is supposed to say delta x sub k. Hopefully I fix that someday. Delta x sub k, which is x sub k minus x k minus 1. And again, it's just the width of each interval. That's all delta x sub k is. We'll just write that up here. It's the width of each interval. We can form the Riemann sum S sub p equal the summation from k equal 1 f of c sub k delta x sub k. But again, what you really need to remember is a Riemann sum is just the idea of adding up the areas with the word area in air quotes, because when I'm below the x-axis, this is going to be a negative product. Height times width there, height times width here. Because we're negative, that f of c sub k value is going to be negative. These give me negative results. But all a Riemann sum is adding up the areas of rectangles. That's all it is. So when someone says Riemann sum and they throw all this scary notation at you, it's just adding up areas of rectangles. That's all it is. Adding up areas of rectangles, keeping in mind that when it's below the x-axis, it's going to be negative, and so it really isn't area, but we'll allow the use of the word area. Some videos I've seen call it negative area. That just makes me cringe to say negative area. Important features about Riemann sum include: need not have the same width intervals, rectangles, need not pick a consistent point within each interval to use to find the height of the rectangle. Region may be above and or below the x-axis, so Riemann sums don't necessarily represent area. They don't. Some definitions here. Let P equal x naught, x1, x2, x3, dot, 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 up to xn, such that A equals x naught is less than x1, less than x2, less than x3, so on, be a partition of the interval AB. The norm of P, denoted by that little symbol there, that's just called the norm of P, is the largest subinterval. So when I've whacked my basic interval into subintervals, the norm of that partition is the largest subinterval. So looking at this picture here, it looks like the norm of this partition would be this width right here, that the norm is just the largest subinterval. So the norm of this partition up here looks like it'd be that guy there. So norm is just the largest rectangle, the width of the largest rectangle, basically. Now we get to a definition which you absolutely do not have to memorize. Definition. Let f of x be a function defined on a closed interval a to b. We say the number I is the definite integral of f over the closed interval a, b, and that I is the limit of the Riemann sum k equal 1 to n of f of c sub k delta x sub k if the following condition is satisfied. Given any number epsilon greater than 0, there corresponds a delta greater than 0, such that for every partition P equal to x naught, x1, to xn of the interval, closed interval a to b, with the norm of partition less than delta, and any choice c sub k in the interval x sub k minus 1 x k, we have that the absolute value of the summation from k equal 1 of f of c sub k delta x sub k minus I is less than epsilon. So there's the official definition of this new thing that we're going to be talking about, the definite integral. And then it continues. When the above definition is satisfied, we write that the limit as the norm of p goes to 0 of k equal 1 to n of f of c sub k delta x sub k equals the integral from a to b of f of x dx. If we are using a partition where all intervals have equal widths or equal width rectangles and have a common point in each rectangle, we write the limit as n goes to infinity of k equal 1 to n of f of x sub k delta x sub k equals the integral from a to b of f of x dx. So here's a new thing called the definite integral. By definition, what the definite integral is the limit of a Riemann sum. When we say the norm of the partition going to 0, remember norm was just the largest rectangle. It was the width of the largest subinterval. We'll call them rectangles. It was the width of the largest rectangle. So it's saying let this largest rectangle go towards 0. So it's doing the same thing that we did last time of taking those rectangles and shrinking them down till they're just line segments. The difference here is that the rectangles don't all have to start out the same width. They can start out various widths, but eventually we shrink the biggest one down to just a line segment, and then we add up all those heights of the line segments. And then because some of these guys could be below the x-axis, our overall result doesn't have to be positive. And so all the definite integral is, I shouldn't say all, but what the definite integral is it's the limit of a Riemann sum, again, where we have infinitely many rectangles. It's a limit of a Riemann sum. And so it is taking those infinitely many rectangles, making them skinnier and skinnier and skinnier until they're line segments, and then we add up the lengths of infinitely many of those line segments. But because some of those line segments can be below the x-axis, the answer can come out to be negative, and if an answer comes out to be negative, it isn't area. So Riemann sums and definite integrals do not have to represent area. Now we will talk a whole lot in the future about ones that do, definite integrals that do represent area, but in general, definite integrals don't have to represent area. But what I want you to carry away from this definition is that the definite integral is a result of a limit of a Riemann sum, and a Riemann sum is that idea of adding up areas of infinitely many rectangles. Note, a definite integral equals a number. That is, the integral from a to b of f of x dx equals a number. We have already talked about indefinite integrals. An indefinite integral equals a function. An indefinite integral is an antiderivative. That is, the integral of little f of x dx equals capital F of x plus c, where capital F of x plus c is the most general antiderivative. So we're hoping, beyond hope, that there's going to be a connection between this guy that has limits of integration, a and b are limits of integration, the integral from a to b of f of x dx, which equals a number, and what we've already practiced quite a bit, indefinite integrals. The integral of cosine was sine. And so hopefully there will be a connection between the two of them, but we don't know that connection quite yet, but we hope there will be. Terminology. The integral from a to b of f of x dx is read the definite integral from a to b of f of x dx. Most people do not put the word definite in there because when you say from a to b, when you state the limits of integration, you are thus telling your reader that it's a definite integral. So a lot of people aren't going to say the word definite just because when you say from a to b, you've told your audience that it's a definite integral. The a and b are called limits of integration. The dx is called the differential, and the f of x is called the integrand. Okay, some silly little problems. Express the limit as a definite integral. So all these things are trying to do is trying to drive home the relationship between limits of Riemann sums and a definite integral. So this part right here, all of that is represented by the integral sign. And so now here's a little thing. It's an elongated S. Summation, elongated S. Now, I don't know for sure if that's why they picked elongated S. I actually have no idea. I just always kind of, hey, this is a summation, this is elongated S, maybe there's a relationship. I'm not really sure there's a relationship or not, but I think it's kind of cool there. So the limit as the norm of p goes to 0 of the summation from k equal 1 to n, that is all replaced by the integral symbol. The interval gives us our limits of integration. Then our function here becomes 2x cubed, and then that delta x sub k, the delta x sub k is replaced with the dx. So there is the definite integral that would represent that limit of that Riemann sum. And so now you do start, when we did indefinite integrals that do not have the limits of integration. And there was that dx thing on the end. And I said, well, that has to do with notation. You'll see why later. That dx is representing that delta x. That's where that dx comes from. Same idea here. So all of that goes to the integral sign. My interval gives me my limits of integration. Then you have the function where the c is just represented, is changed to an x, because the delta x sub k is telling you what the variable really is going to be. And then dx. So not hard problems here, but just trying to get the point across, the relationship between Riemann sums, limits of Riemann sums, and definite integrals. Now, unfortunately, we're going to need to do a definite integral the long, hard way. So that is what we're going to do next. Compute the following definite integral as a limit of a Riemann sum. Now, those of you that have had calculus before know there's a way easier way. You can't use the way easier way till we get there. But once we get there, please don't go back and do this. So, the integral from 0 to 3 of 2x squared plus 1 dx. So we're going to do very similar to what we did the last section as far as doing area. We may choose any partition and any within each subinterval. So we are going to choose right-hand endpoints and equal width intervals. Riemann sums can be anything, any partition, any point in each subinterval. Since they can be anything, you can pick the one you want. So we're going to pick equal width rectangles and right-hand endpoints. So the first thing that I did was draw a picture of 2x squared plus 1. And my picture might be a little bit off, that 2x squared plus 1 looks like maybe it's coming to the origin, but give me credit, don't worry about that. So there's my function, and I drew in my rectangles, equal width. There's my representative rectangle with each rectangle meeting on the right, because that's what I chose. Riemann sums can be anything. I chose something equal. We will continue on with this problem in the next video.